Today, whoops, I need to freeze this in. Sorry about that. There we go. That's better. Today we are going to cover section 2.3 in our textbook. We're going to talk about forces and equilibrium in a plane. Now, the work that we do today builds really directly on the work that we've done in sections 2.1 and 2.2. But before we get started, I want to show you a little bit about our Moodle page, just so that you kind of can see how everything is coming together. When you go to your student portal and you go under the Moodle logo and choose statics, you'll see that the lectures that I have recorded and that are available to you embedded in Moodle have a link out to the left. So when you come down a little bit farther, you'll see, for example, statics lecture number 2 has a link to the left, 3, 4, and 5 have links to the left. But statics lecture number 6, which is what I'm doing today, just has an assignment icon next to it. Now, that's because the content isn't recorded. That's actually what I'm going to record today. So this is just a placeholder so that you're able to see where we're going and what to expect over the next little bit. But after I record the lecture and it processes, I'll replace it with the link, and then you'll have access to that lecture as well. But that's sort of the way that it works. Now, if you go then to the word submit for homework for chapter 2, and you look at the homework under chapter 2, we have the first homework set and the second homework set. Those are taken from the first 2 lectures of chapter 2. After we're done today, I will add a third homework set, which will be for the material that we cover today. So in other words, this is like a running total of what we're doing in class. None of it will be handed in until the due date, which is September 13th. But I keep that running total for you because I want you to be able to keep up with your homework, and also to know that there's like a finite amount. I'm not going to spring on you like, oh, I want to do 5 more problems in section 2.1. That's the entirety of the homework for section 2.1 unless something significant changes. Now, also next Friday, we will have a quiz over chapters 1 and 2. It's not available yet. It will be available toward the beginning of next week if you finished your homework and you wish to take it early. But this quiz, there's only 2 quizzes. There's one after chapter 2. Then we'll have our midterm exam, which is face-to-face proctored or online proctored if you're not here in Powell. And that will be after chapter 4. But then after chapters 5 and we do 5, 9, and then we come back and do 6, 7, and 8. But after 5 and 9, we'll have another quiz. But there's only 2 quizzes. And the quizzes are not proctored, but they're timed. So in other words, sometime before midnight on September 13th, you'll open this link. There will be a quiz available to you. You'll fill it out. And then the answers will come back to me through Moodle. At the same time, you will take a picture of your quiz work and email it to me, and that will be part of your grade as well. But all of that has to happen in a time frame. So I can see when you open the quiz, and I need to get the completed quiz plus the material that you worked on that you take a picture of and email to me within an hour of opening that quiz. Okay? So the elements, that's sort of the elements of grading. There's going to be 8 or 9 homework assignments, 2 quizzes, a midterm exam, and a final exam. But the only thing that are proctored are the midterm exam and the final exam. All right? So anyway, so the Moodle page changes every time that I put up another link, and every time that we're ready for another homework set. All right, do you guys have any questions about that? Excellent. All right, well then, let's take a look at section 2.3. And 2.3 is entitled Forces and Equilibrium in a Plane. So what we're talking about then is we've already been talking about forces. We've mentioned equilibrium. And when we say in a plane, we just mean we're not going to go into 3 dimensions yet. So the plane is just that 2-dimensional surface of the piece of paper or the chalkboard or your notebook or whatever. And so we're just talking about I decided there's 2 Y's today. There's an x direction in the horizontal, y direction in the vertical, and we resolve into these components. All right, so some of the things that we know are that in order for a particle to sit still, in order for a rigid body or particle to remain at rest, the sum of all the force vectors acting on it have to equal 0. So in other words, let's see if that's it. No, I can't make that. Just doesn't look very good. So in other words, if the sum of the forces is equal to something other than 0, the particle is going to move. And so this is the condition for static equilibrium. It's also the condition for moving with a constant velocity, but in this class we're more concerned with things that are not moving at all. So this has to be true. There are other things that have to be true as well, but this is the first big building block. So how do we determine if the summation of forces in all directions are equal to 0? Well, we break it into vectors, and generally speaking, we can then say that the summation of forces in the x direction is equal to 0, and the summation of forces in the y direction is also equal to 0. And we determine all of those forces by drawing a free body diagram. So in general, a free body diagram, I like to tell people it's sort of like a very narcissistic view of the world, where there's one item that is the center of the world and everything else is acting on that center. So if we have an object, a box or a pulley or a weight, we consider that to be the center of the universe, and everything else that's acting on it is a force acting on that particular body. Now that's the solution technique, and that's what we're going to use not only today, but pretty much for the rest of the semester. So it's really important that this becomes second nature to you. It will not necessarily be second nature today, but as time goes on, it will become more and more like that. So I'm going to work a few problems to sort of bring out this idea. And the first one I'm going to work out is 2.43 in your textbook. So make sure I don't have that down on the assignment list. Okay, good. All right, so 2.43 looks like this. We have two cables that are tied together, and they are connected up to the ceiling by brackets at point A and point B. And they meet at point C. And from point C, we have a weight suspended, and the value of that weight is 400 pounds. So this is not a free body diagram. This is just a diagram of the problem statement. We're told that this angle is 50 degrees. And we're told that this angle is 30 degrees. It's also very important to note that the problem says these are two cables tied together. If it was a single cable that just went through a loop at C, the magnitude of the tension in both would be the same. But since it's two different cables, the tension values can be the same. So it says determine the tension in cable AC and the tension in cable BC. So the first thing I want to do is to draw a free body diagram. And the free body diagram that I would like to draw is just acting on point C. The reason for that is that then we have a tension in AC pulling up and to the left, a tension in BC pulling up and to the right. And as far as this point C is concerned, what is the weight doing? It is. It's pulling it straight downward. And so this is a free body diagram in that we have a point and then everything acting on the point. So what do I know? In order for this to be in static equilibrium, I know that the summation of forces in the x direction has to sum to 0. Yep. And the summation of forces in the y direction also have to sum to 0. So I have two equations. Algebra tells me that if I have two equations, I can solve for two unknowns. And I also have two unknowns because I know that my weight is equal to 400 pounds. All right, the other thing about the weight is it only acts in the y direction, so it's not going to be a factor in the x direction equation, is it? But we do have the summation of force in the x direction. In order for it to sit still, has to sum to 0. So I have some component of TAC in the x direction, and I have some component of TBC in the x direction, and they sum to 0. And in the y direction, also sum to 0. I have some component of TAC in the y direction, some component of TBC in the y direction, and I have the entirety of the weight. And those pieces also have to sum to 0. All right, now to determine what those components are, let's look at TAC first of all. I know that the angle that TAC makes with the horizontal is 50 degrees. I also know, if I look at the vector, it points up and to the left. Up means that its y component is positive, but to the left means that its x component is negative. If I look at BC, it's positive in the x and positive in the y, isn't it? And what about the weight? Is it positive or negative in the x direction? Perfect. It's negative in the x. All right, now I need to figure out what those components are. Well, if I look at TAC and I have this 50-degree angle, I know that the adjacent and hypotenuse are the cosine. So TAC in the y direction, which is right here, is going to be the entirety of TAC, the tension in AC, times the cosine of 50 degrees. And TAC in the x direction is negative, but it's going to be that hypotenuse, which is TAC, the entirety of the tension, times the sine of 50 degrees. For BC, the tension in BC pulls up this way, and I am told that this angle is 30 degrees. So TBC in the y direction, oh, I did that backward. You're going to have to excuse me just a moment. If this is opposite, so this is the sine, and this is the cosine, isn't it? Because adjacent hypotenuse is sine. So adjacent to that angle is the x component. Opposite that angle is the y component. Okay. So similarly, TBC in the y direction, I'm looking for this component. This angle is 30 degrees. That's opposite. So it's going to be TBC times the sine of 30 degrees. And TBC in the x direction is TBC times the cosine of 30 degrees, because cosine is adjacent over hypotenuse. All right, so now I have my pieces of the puzzle. I'm going to fill them in down here, and then we have to rely on my ability with a little bit of trig and some algebra in order to solve for the values of TAC and TBC. All right, so TAC in the x direction is I have to remember my negative sign, TAC times the cosine of 50 degrees plus the part of BC that's in the x direction. And those two things add together to be 0. I have one equation and two unknowns, so I can't solve that explicitly, can I? Not yet anyway. I will be able to. In the y direction, TAC in the y direction is TAC times the sine of 50 degrees and TBC is TBC times the sine of 30 degrees, and I have minus the weight, which is 400 pounds, and those three things sum up to 0. All right, now I have two equations and two unknowns. I can solve these simultaneously using any technique, but the easiest to me looks that I could solve this equation for either the tension in AC or the tension in BC in terms of the other one, and then substitute it into this equation. How does that sound? Right. So I'm going to take my x direction equation, and I'm going to solve this for TBC. So TBC times the cosine of 30 degrees equals, because I'm going to bring this term over to the other side, TAC times the cosine of 50 degrees. The TBC then is equal to TAC times cosine of 50 degrees over cosine of 30 degrees. All right, so this is just a number. I don't know what it is yet, but I can find out on my calculator. And I think I had told you this before. Make sure that your calculator is in degrees, not radians. If you're in radians, you'll get silly answers that won't be correct. So I'm just checking mine is in degrees. Okay. See if we can get it off or not, huh? All right. So now I'm going to take the cosine of 50 and divide that by the cosine of 30, and there's my coefficient. The divided quantity is 0.74227. So that means that TBC is equal to 0.74227 times TAC. I'm going to use this quantity to substitute back into the other equation so that I have only one equation and one unknown. Okay, so I have TAC, I'm using this equation, times the sine of 50 degrees plus TBC, but I'm not going to call it TBC anymore, I'm going to call it 0.74227 times TAC times the sine of 30 degrees minus 400 pounds equals 0. Or I'm going to take that 400 pounds and pull it over to the right-hand side of the equation, at which point it becomes positive. So I'm going to find the numeric value for the sine of 50 degrees. And that is 0.76644. So in other words, I can say that this is 0.766 TAC. And over here, I need to take 0.742227 times the sine of 30. So the sine of 30 is 0.5. And when I multiply that by 0.742227, that's the coefficient for TAC in this piece, 0.3711 TAC equals 400 pounds. Since these are both terms in TAC, I can add them together. And I get 1.137 times TAC equals 400 pounds. So I can divide through by 1.137. Divide 400 by 1.137 to get the numeric value of TAC. And let's see, 400 divided by 1.137 equals 351.8, which rounds to 352 pounds. So my value of TAC is 352 pounds. Now to find the tension in BC, I don't have to reinvent the wheel. I can go back to this step and just multiply TAC by this value, and I'll get the value of TBC. So if you keep your work nice and organized, that's another advantage. You don't have to go back and redo everything. So I just do this. So I take 352 and multiply it by 0.742227, and my value of TBC is equal to 261.1 pounds. All right? And so that's how we can use the trig that we've built up in sections 2.1 and 2.2, along with a free body diagram and the equilibrium equations, to solve for the tension, to solve for two unknowns. So do you guys have any questions for me at this point? And you can see how this all builds, right? I mean, everything builds on everything else. So it's pretty cool that way. So I am going to work one more problem because it's 12:22, so we have a little bit of time. And the setup is going to be the same. You just sort of have to analyze the problems based on sort of the geometric configuration, the trig of the problem, and what they're asking for. But the basics are all the same. The summation of forces in the x have to equal 0. The summation of forces y have to equal 0. And you have to use your trig functions, and that's about it. So everything else works the same. So let's look at problem 63. 263 says we have a collar and it's connected as shown to a 50-pound load. So the most challenging part is drawing these, if you're like me. Hopefully you're a better artist and you don't have the difficulty. But basically we have a pulley here at B, and we have a cable that wraps around the pulley, and we have a weight suspended from the pulley. Below this, we have a rod, and on the rod, we have a collar at A with a hook in it, and the rope hooks around the pulley and latches onto the collar. Now, you can see that if we let everything go, the collar A would slide right underneath the pulley. But we have a force P that we're pulling on it with to keep it in place. We're also told that the weight is 50 pounds, that the distance from here to here, all the way down, is 20 inches, and that the distance from A to B, from here to here, is unknown. All right. And it says collar A is connected as shown to a 50-pound load and can slide on a frictionless horizontal rod. Determine the magnitude of the force P required to maintain equilibrium when x is 4.5 inches and again when it's 15 inches. So first time it's 4.5 inches. Second time it's 15 inches. So that's going to change my angles, isn't it? All right, so the first thing is we can think about what's going on here at point A as a free body diagram. And we have a force P pulling this way, and we have some tension in this cable AB, And we also, if you think about it, have some sort of a vertical force of the rod pushing down on the collar. This is not a particularly interesting force. It's just a reactive force of the situation. But this is what's going on at A. What's going on here at B? Well, we have a 50-pound load pulling down, and we have that same tension in that cable A to B, and then we also have some reactive force here at B that's keeping the pulley attached to the ceiling. Now, the interesting part about this is, or the thing that makes this problem work, is that TAB in this free body diagram and TAB in this free body diagram have the same magnitude, right? Because they're essentially the same force. And the other interesting part is, if you think about the weight, point C, as being a free body diagram, if this is not moving, if this is pulling down with 50 pounds, this is pulling up with 50 pounds. So what that means is the tension here in this cable is 50 pounds, and since it's the same cable, the magnitude in the tension here is also 50 pounds. See how that works? That's all a pulley does, is change the direction of the force. Okay? So that means that we know right off the bat that this is equal to 50 pounds. All right. So if we look at this problem then, after we do that analysis, it's relatively simple. In case I, where the x value is 4.5 inches, when I draw this out, I have a triangle that looks like this. I know that the distance from here to here is 20 inches. And I know in the first case that the distance from here to here is 4.5 inches. So I can say then, the only two forces I have acting on point A in the x direction are the component of TAB and the force P. So I know that TAB in the x direction minus P have to equal 0. This is true for both cases, but the angle is going to be different. So what is TAB in the x direction? Well, in case I, if this is TAB, I want the piece in the x direction. And so we can construct a triangle. I'm going to do this the long way. Basically, if this is 20 and this is 4.5, this angle theta, the tangent of theta is the opposite over the adjacent. So that means that the angle theta is the inverse tangent of 20 inches over 4.5 inches, or the inverse tangent of 20 divided by 4.5, because the units go away, of the inverse tangent of 4.44. So I've got that number, and I can say second, that's tangent to the minus 1 of my answer. That angle in the first case is 77.3 degrees. All right, so in the x direction, that's adjacent to that angle. So TAB, adjacent over hypotenuse, is cosine times the cosine of 77.3 degrees minus P equals 0, or equals P. I also know that my tension is 50 pounds. So if I take 50 pounds times the cosine of 77.3 equals P, I can find it right away. So I take the cosine of 77, it's 0.2195, multiply that by 50, and I get a value of P of 10.97, or roughly 11 pounds. Now in the second case, and I'm also making a case for staying organized, because in the second case, all I have to do is to change this number from 4.5 inches to 15 inches. So if I've stayed really clear on my work, I don't have to reinvent the wheel. Okay, so I still know all of this is true, except for now my tangent is going to be different. In this case, theta is going to be the inverse tangent of 20, not over 4.5, but over 15. So if I take 20 divided by 15, that's 1.3. I take the inverse tangent of that value. I get the angle in this case is 53.13 degrees. Okay, so just like that, here I can say, I can say TABX minus p equals 0, TAB not times the cosine of 77, but now times the cosine of 53.13. I can say 50 pounds times the cosine of 53.13 degrees equals P. That's 0.6 times 50 is 30. So in that case, P is 30 pounds. All right. So does that also make sense if you think about it? The farther you pull that collar out, the larger force you're going to need, isn't it? Because it's going to want to snap back over to being directly underneath the pulley. So the further you pull it away from the pulley, the more force you're going to have to put on it to keep it there. All right. Do you guys have any questions about that problem? Oh, that was in the problem. It said determine the magnitude of the force P required to maintain equilibrium. The first part when x is 4.5 inches. Second part when x is 15 inches. Yep, good question. All right. So I'm going to pull this out of my book because there's just one more thing I want to show you, and my drawing skills fail me at this point. We're just going to talk a little bit about pulleys. Okay. On 67, 2.67, we have a series of pulleys and ropes, all supporting a 600-pound crate. And the problem says, for each arrangement, determine the tension in the rope. Well, the way that you do this is you think about how many ropes are pulling up on the box. So in other words, if you had a 600-pound box, and you had one rope pulling it up and it was in static equilibrium, the tension in this rope would have to be 600 pounds, wouldn't it? But in this case, look at the first one. You have two pulling up on it, don't you? So each one of those, what do you suppose the tension is going to be? Yeah, 300 pounds. Perfect. Now here, even though there's 3 ropes, there's only 2 that are pulling up on the box, right? So once again, the tension in that is 300 pounds. Very good. What about here? We actually have 3 ropes pulling up, don't we? Yep, they're 200. And here, 3 ropes, 200. And here we have 1, 2, 3, 4. So those are all 150. So this is actually how block and tackle arrangements are constructed, because if you have half the weight, you have to pull twice as far to make it go up because you're pulling twice the rope. So you do the same amount of work, but you actually reduce the force by using pulleys. And that's something they do a lot in industrial applications, especially in olden days, even before I was around, you know. But I mean, to move something heavy or to move something in a position that's difficult for a human being to move, these things can make something go from being impossible to being possible. So one of the things that you'll be called upon when you're doing your homework is to analyze that sort of an arrangement, you know, to decide what the tension is, and sometimes you have to do it based upon the configuration of the pulley system. All right, well, that is it for today, ladies and gentlemen. Later today, I will have, hopefully later today, but as soon as possible, I'll have this lecture posted to our Moodle page, and I'll have another problem set. These problems are getting progressively more involved. So you'll only have 2 or 3 problems a night. You won't have, 15 or like we did on the first one. That would take you forever. So we're just going to tune them down, make sure that every one of them is very appropriate and very helpful. So if you have questions or problems, don't hesitate to come see me. That's what I'm in my office for. Or if you need some time allocated, just send me an email, and I'll set time aside for you. So we'll go from there. All right. Well, you guys have a great day, and we will see you possibly on Friday. And if not,